All right. Does this work? Yeah. OK. So hello, everybody. My name is Pavel. I'm a PhD student at ETH Zurich, and this is a joint work with Mark and my supervisor, Martin. And what I will try to explain in the next 20 minutes is how we can use program synthesis techniques to help developers to create user interfaces more efficiently. And in particular, the problem that we are considering is that if you think about how user interfaces are designed at the moment, you have a designer that tries to come up with a nice design that is usable and people like it. And then there is a developer that literally has to plug everything together. So whatever the designer comes up with, he has to come up and implement in a particular programming language. And if you look at the tools that these two different roles use, the designer so what the designer really does is it produces a visual image of how the application should look like. And for this, he uses or she uses specialized tools such as Adobe Illustrator, Adobe Photoshop, or Sketch that are really designed for this purpose, and they are really designed for drawing. On the other hand, the developer uses IDEs, so he writes codes, and he writes code for, depending on where the application is supposed to run, he might write code for Android or iOS. If it's for desktop, he can use a bunch of frameworks that are designed for desktops, or if it's for web, there is, again, plenty of frameworks that are used to express layouts for webs, and there is a new one coming up every month. And in fact, the developer doesn't often even see what the layout looks like. He has to compile the application and then render it on a device to see, oh, this is how it looks like. I go back to the code and rewrite it. So there is this fundamental gap between these two sides. So there is a designer, there is a developer, and they have to coordinate. And what we try to do in our work is to automate this process. So what if we can help or even replace the developer with a tool that from a specification that the designer gives us synthesizes the implementation for a particular framework. And this solves a bunch of problems that are inherent to this process. So the first one is if a developer has to do this manually, the developer can make mistakes. And the reason why the developer can make mistakes is if you consider the problem is that you are not creating layout for one device, but you're actually creating layout for a lot of devices. So for Android, you have to take, if you design something for Nexus 4, you have to take into account all the devices that have, for example, smaller size or bigger size. And there are not only two examples or two devices as in this picture, but in fact, for Android, there is almost 10,000 different devices that you have to support, right? And this creates a lot of effort on the part of the developer that has to figure out the way how to do this. And to show you concrete examples of what can go wrong, imagine this is how the designer designed the application, and if you render it on a small device, suddenly you see that these two things are clumped together. And the margins are not preserved. Another example of application called Amigo, if you render it on a device that is smaller, suddenly the text and the image start overlaying, so it's hard to read what the text is. And in the final example, there is an application called Candid that has quite an important button that says start using the application. And if it's in a small device, you can barely see the button, right? So it would be even smaller. You would just not even know how to start using the application. And OK, so this is one thing. Another thing is that there are often multiple ways that we can implement the layout. So imagine you are implementing a very complex application, such as Mozilla browser. And if you use a naive implementation, it can be very slow. Maybe a better implementation can be a bit faster, and even better implementation can be very fast. So again, the goal of the developer is to optimize the implementation, not just to have an implementation that looks like the input. And finally, if you have such a tool, it's quite useful for porting. And the porting is not only for different platforms. So I have an Android application, and I want to use it on iOS, but also within an individual platform. So for example, on Android, there is a new layout system called ConstraintLayout that improves in many aspects. But since it's new, it's in fact used only by 2% of the applications. And there are still 98% of the applications that are still using the old layout system. And if you have a way to translate between the two, you can immediately speed up half of the application on the App Store with no effort on the part of the developer. And finally, there is just this problem of having two people doing unnecessary work, having two specifications and things like this. So how can we address this problem? So the standard approach used by machine learning, and there is some prior work on this, would be to say, well, we have a lot of applications already on GitHub or on Google Play, and we can just render them. This gives us a data set that matches the implementation and how it looks like, and then we can just put a neural network in between and try to learn as best as we can to solve this task. But this has several problems. So first of all, if you try this model, they are not even syntactically correct. So the code that it will produce might not even parse. They have no formal guarantees about whether the layout they produce is actually satisfying the input image. It's just probabilistic. And it's not clear how would you encode a lot of robustness properties that would prevent all the layout errors I've showed earlier. And it's also not clear how would they incorporate user feedback. So instead, in our work, we consider more traditional programming languages approach, where we say, well, we really want to do layout synthesis. And for order to do this, you need first an algorithm that does the synthesis. The algorithm needs to know what is the formalization of the language over which we are synthesizing. It will be able to encode a set of robustness properties that I will describe. It will also need to take into account that the input is, even though the input is only a single device, the layout that we want to synthesize should actually generalize to a lot of devices. And inherently, because of this, it can happen that we can make mistakes. So we would like to have a way to incorporate user feedback that tells us if something went wrong, we can, again, synthesize with improved specification. And finally, there is still all this code available, so we would like to take advantage of it. So we'll have a probabilistic model that helps us both speed up the synthesis and produce layouts that generalize better. So we implemented this system. It's called InferUI, and it's implemented for Android, and I will walk you through the individual parts. And I will start with the formalization of the layouts. So in Android, you can think of a view as having sort of 5 different points that describe the view, and these are the top, bottom, left, and right edges, and the line on which the text view sits. And if you have these points, you can try to position views relative to each other, and this is what the relational layout here stands for, that to position views, we relate them to each other. So for example, if you want to put the view B to the right of view A, we could say align left edge of the view B to the right edge of the view A with some margin, right? And the semantics of this can be captured with a linear constraint that says exactly this, right? So the left edge of the view B is the right edge of the view A plus some margin. Now, if we set the margin to 0, this would correspond to this. So the views are just next to each other. And you can ask a question, well, what if I want to have something like this? So the view is a bit to the left, which would require negative margin, but this is actually something that the layout already doesn't support. And if you want to have this in the application, this is where the developer would have to already figure out a way how to go around the limitation of the layout system. There are also more complicated constraints. So for example, if you want to have a view be in the center of 2 other views, you can have a constraint like this. You can have it in the center with respect to some margin, or actually it doesn't have to be necessarily precisely in the center. You can say, well, put it in the 25% of the center. You can also support constraints that have the dynamic size of the view. So you can say, well, put the view B in between A and C, but stretch it as far as possible, right? And the important thing to take away here, and also you can have a constraint that says, well, put it at some angle and a distance, right? And the important thing to take away here is that all these constraints can, in fact, be described with the linear constraints. And it's not quite important what these linear constraints are, but we can write them down. And we did this for all the 26 types of constraints that can be used in Android. And in fact, in doing so, we even find out some errors in the Android system where the specifications didn't match what the documentation said. So with this, we can move on and say, well, OK, if we had a specification, how do we go about synthesizing layouts? And to start with, let's first think about how do we solve the layout. So if the user already written the layout, what the device has to do is to figure out all the positions of the edges of the view such that it can be rendered on the device. Because once you know the position, you can just render it at that position. So suppose we have these two views, and the goal of the solving is to figure out the absolute position. And to do this, we have some constraints that the user had to write. And the user doesn't write the constraints like linear equations. There is some language that internally translates to these equations. So we have these two constraints. Well, can we, and they constrain the position of this view. So it says the view B is to the right of view A, and A is to the right of the screen. But using only these two constraints, we cannot actually compute the absolute position because this is just not enough information. What would help us if we know what is the position of the screen. So we know that the left edge of the screen is at coordinate 0. The right edge is at 240, which means that the width is 240. And with this, we can already compute the left edge of the view A. But we still cannot compute more because we don't know the size. So for this, we need additional constraints that say, well, the view A is actually, the width of the view A is 80, which we can compute by subtracting the right edge with the left edge. And with all these constraints, we can compute all the absolute positions, and we can render the layout. And now the goal of the synthesis is exactly the reverse, right? If the user gives us the absolute positions, what are all the constraints that we should write here, such that if we solve for them, we would get the numbers that the user wanted, right? And the way we can solve this problem is by encoding the synthesis problem as a logical formula. And then we solve the logical formula, and the solution to this will tell us what are the constraints and what are the sizes. So how do we go about this? So the formula looks roughly like this, and it has three parts. So we first have to encode the input specification that the user gave us. We then have to encode the constraints, and then there is some part that ensures that the constraints that are selected are actually valid. So the encode input specification, this is pretty simple. So the user just gives us the absolute positions of all the views, and we just set them to these values as the user wants. Now to encode the constraints, you can think of, well, what are all the constraints that I can use to relate view B? And I can just go and enumerate them. So I can say, well, the view B can be to the right of view A, or it can be to the left of the screen, or it can be in between, and so on. And there is, in fact, number of views squared of such constraints because of the centering constraints that always relate two views with each other, right? But we can just enumerate them. And then the goal of the synthesis is actually to pick one constraint out of all of these that will be used, and that satisfies the input specification. And to encode this as an SMT formula, what we'll do is we will add an implication for each of these constraints. And on the left-hand side, we will introduce a new Boolean variable where the intuition is that if this Boolean variable is set to true, then this constraint should hold. If it's set for false, the constraint doesn't hold. And then the encoding just says, go for all the constraints for a given view, add such an implication, and then ensure that only one of those implications is going to be true, which is what we want. And then if we solve for this, by just looking at these Boolean flags, we know which constraints we should use. And we do this not only for one view, but we actually do this for all the views. So this is the encoding of the constraints. To ensure that the constraints are valid, we have to just ensure that all the constants are valid, so all the margins are less than equal 0. If there is an angle, it has to be a valid angle. And we also have to ensure that the constraints are actually valid. So for example, you cannot have acyclic dependencies because then you cannot resolve them. And we can then use any off-the-shelf SMT solver. And if you solve this formula, we get the solution. Now the question is, well, are we really done? And the answer, unfortunately, is no. And the reason is that if you do this, it doesn't scale. So it works for up to 4 views, which is not really useful for the developers. And it actually doesn't generalize very well. So the layouts we synthesize work on the device. I mean, they satisfy the input specification, but they don't generalize to other devices. And this is not surprising because nowhere in this formulation we talk about other devices. So why should they generalize? So to fix this, we will do 2 things. We will show how to extend this to multiple devices. And we'll also show how can we fix the scalability. And finally, we also briefly talk how to incorporate user feedback. So to start with, if we want to generalize better, we can think of, well, let's not synthesize any layout that satisfies the input specification. but in fact synthesize the most likely layout that satisfies the input specification. And the most, so we are going to change, instead of doing a satisfiability, to maximum satisfiability. And the cost we are going to use is, suppose that there is some probabilistic model that tells you what is the probability of each of the constraints. And we are just trying to maximize the select constraints that maximize this model. And by doing this, we can already improve the generalization much more because of how this probabilistic model is going to be learned. So we'll learn it from existing applications. And also, this helps us to scale the system much better because it's not shown here, but if you have the probabilities of the constraints, you can use them to guide the synthesis to consider the more likely constraints. So what does this probabilistic model look like? So intuitively, if I have these three constraints, it should tell me that which one is the more likely, or assign a probability to each of them. And in this case, it should be this one, because somehow it's symmetric, and it makes sense that this is aligned to the left and this is aligned to the right. But the tricky part here is that if I move this view, actually the most likely constraint is going to change. So in this case, it's going to be this one. And if I move the view even further and I put it below, the most likely is going to be this one. So it really depends on the context in which you put the views. And to attribute for this, we have a model that is based on a set of relatively simple feature functions. For example, one feature function could be, what is the distance between two views? Or what is the constraints that we use? Like, am I relating these views from left to right or from right to left? Or if I were to draw like imaginary line that shows the constraints, how many of other views will it intersect? And we have a bunch of these feature functions, and we can train all of them using maximum likelihood estimation, and then the probabilistic model overall is just a weighted combination of all of them. And with this, now how do we actually generalize to multiple devices? So intuitively what we want to do is you just synthesize a layout using the input specification for a single device. Then you render it on multiple devices, and then you check if there are any errors on any of these multiple devices, right? And it turns out that you can encode all of these parts as a formula. So the synthesis is already a formula. To render on a multiple devices, this is just a different formula that does the opposite way. And we can also define a set of robustness properties that range over the variables in these two formulas. And then we can encode them all as a single formula that is, again, fed to the SMT solver. So this loop is actually done internally in the solver. What about the feedback? So if we synthesize a layout, maybe this view was not supposed to be like this, but it was supposed to be a bit shorter. So how can a user give us or tell the system that this was a mistake? And it turns out that in our formulation, this is really trivial. So if the user just give us this view as additional input specification, we can just extend the formula with the position of this new view, and nothing else changes, really. We can use all the machinery we described so far. So to evaluate our project, we looked at the top 500 applications, both on Google Play and GitHub. And if we try to synthesize layout, so this just shows the number of views in the layout and how many of them we can synthesize and what's the time. And we can see that for a single device, we essentially always succeed. The more difficult part is what happens if we consider multiple devices. And we can see that it still works reasonably well, and it's still very fast. And the problem here is that often, if you have multiple devices, there is just no layout that satisfies all the robustness properties that we have. So you would have to actually split the implementation into different layouts to cover all the devices. What about the view generalization? So I showed you at the beginning, if you have the naive implementation that just considers the input for a single device, it doesn't really generalize that well. If we add a probabilistic model, it already improves to 75%. If we add the robustness properties, this is actually 92%. So 92% of the views are at the positions that are supposed to be on multiple devices. And then we can also try a user experiment that says, if we do this loop and now show this to the user, and the user tells us what was wrong, and we synthesize again, how many of these loops do we actually need to do? And it turns out that in 62% of the cases, we immediately get the right thing. In 5% of the cases, we need one feedback, and in 8% of the cases, we need two feedbacks. And finally, although this is not the main contribution of our approach, if we have such a set of robustness properties, we can actually check for errors in existing applications. And we can see that some applications actually don't have problems with restricting the margins and preserving the order and other things. So this is the system, and hopefully you can use it soon in your ID if you're developing applications like this. So with that, thank you for listening, and I'm open to questions.
Thanks. So an earlier version of Interface Builder did probably a simplified version of this in which they automatically inferred constraints based on the user manipulating positions of various views. And the problem was that not only did it rarely generate the right set of constraints, but when it generated the wrong set of constraints, it was very difficult to debug because these constraint systems are notoriously hard to debug.
Yeah.
So have you looked into kind of the debuggability of the sets of constraints you're generating?
So no, but we don't need this. And we don't need this because of two reasons. So what we generate is, even though we generate the constraints internally, we translate it to the user code, which doesn't really see the constraints. Because the user doesn't really write the constraints. The user writes like, there are APIs that align these things. It doesn't really write the constraints as we show it in this work. And the other thing is that we try to have a probabilistic model that tries to synthesize the most likely constraints that the user would write. So I didn't really show this, but in fact, if you run this, 62% of the constraints that we generate are exactly those that the user would write.
Right. So in the other, 38% of the cases, right? Like you generate some set of constraints, and then the user manipulates the view, and then it does something surprising. So then the user has to debug the set of constraints, right?
Yes. But I think the main point is that the constraints, there is no new language that we introduced. The constraints are in the same language as the user writes. And if the user manipulates I mean, you're right, that we might want to optimize for, if we have two versions of the layout interface, we might want to optimize for having similar constraints or changing the least amount of constraints to not confuse the user. We didn't do this. Yes, this is a good point.
Okay, thank you.